Welcome for physics lesson. We will be studying the Hooke's Law. I'll start by giving some characteristics of substances, which are very important to know. We continue with the topic. Therefore, the first property of substances which I'll discuss is strength. So the strength of a material is the ability of a material to resist breakage when under forces. Therefore, if a substance is subjected to some force, either stretching it or compressing it or sharing it, and that material can withstand the force, then we say such a material is strong or it has strength. Therefore, the larger the force a material can withstand, the stronger it is. The other property or characteristic we are going to discuss is brittleness. Brittleness. So, brittleness is the ability of a material to resist breakage when under forces. So if you subject a body under some forces and it doesn't break, then we say it is brittle. Number 3, we have ductility. Ductility. So this is where we get ductile substances. These are materials or the ability of a substance to change its shape and size when exposed to some forces. We have some materials like iron, copper. These are materials which can change shape. When something is round, it can be molded to become a straight wire maybe. So such materials which can change their form due to application of some force, they are called ductile substances. We say they are ductile. So the other property is elasticity. Elasticity. A substance is said to be elastic if it can retain original shape once the shape has been changed due to application of a certain force. Let me use an example of a spring to demonstrate elasticity. For example, if we got a spring like this one, this is the original size of the spring. Therefore, if I apply some force, then this spring is going to stretch and increase in size. Once I withdraw the force, which is stretching the spring, it is going to go back to the original size. Therefore, that ability for the spring to go back to original shape and size once a force has been withdrawn is called elasticity. And so we say that this spring is elastic because it can go back to original shape once force has been withdrawn. Allow me now go to stretching of materials so that we may go to what is called the Hooke's Law. Stretching of substances. Stretching of materials. Stretching of materials. So we are going to examine a spring and we see what happens to the shape and the size of a spring when different forces have been applied on the spring. Therefore, we shall start, we shall organize so that we may have the force or the mass which will be causing which will be applied on the spring. We'll have a mass here and the length of spring. Then after that we will have extension. The extension can have it as E. The extension caused by the given mass. Therefore, we will start when the mass is 0. We see what the length of the spring will be. Then again, we had a mass of 50 grams. So mass is in grams. Grams, we check what the length will become. 100 grams, 150 grams, 200 grams, and if possible, at 250 grams. Therefore, I'll organize the setup so that we may see what happens to the length of the spring when different forces have been applied. So this is the setup. We have a stand which is holding a ruler and a spring here. So without any force applied on the spring, we can see its length. Its length is from 30 to 35.2. From 30 to 35.2. Therefore, 5.2 centimeters. Therefore, the original length, when no mass has been hung on the spring, is 5.2 centimeters. 5.2 centimeters. Therefore, now we can check what the length of the same spring is going to be when we hang a mass of 50 grams. Therefore, this is a mass of 50 grams, and we are going to hang it on the spring, and we will see the new length indicated. There is some stretching, and it reads 38. It reads 38. Therefore, without any mass hooked, it had read 35.2. Now, when 50 grams have been hung, it is reading 38.0 centimeters. So we can check what it is going to read when a mass of 100 is hooked, or when we had another 50 on the same spring. Therefore, we can add another 50 gram, the same spring. So it has stretched again to 42. To 42. So now the new length is 42.0. 42.0. 42.0. We can also check when another mass of 50 has been hung, adding it to 150 grams. The stretching has again increased. Yes, that is it. So the stretching has again gone from 42. It is now indicating 46.2. 46.2 centimeters. That is the new indication of the length. So we can check again where the spring will go when we add 200 grams. So the length of the spring now goes to 50.4. 50.4 centimeters. Lastly, we can add another 50 grams to see what the length will be when we have 250 grams hanging on the spring. So now, using a mass of 250 grams, the length of the spring goes to 54.5. 54.5 centimeters. So now we have seen the different extensions by the different sizes of masses. Therefore, we can now create extension in each case. We can now check the extension. Therefore, now when we hang no mass, the reading was just 55.2, 35.2 that is, and no extension which was caused on the spring. But now, when we added 50 grams, the length of the spring went to 38.0. Therefore, there is an extension which has been caused on the spring. Therefore, original size of 35.2 minus 38 gives us an extension of 2.8 centimeters. Again, we are seeing that when we added another 50 so that the mass becomes 100 grams, the extension went to 42. Therefore, from original 35.2 to 42, we have 6.8 centimeters as the extension. When we the force causing the extension to 150 grams, we can see the length went to 46.2. Therefore, 46.2 minus the original 35.2, we can see the extension going to 11.0. When the mass went to 200 grams, the extension became, or the length became 50.4. Therefore, when we subtract from original length, we have 15.2 as the extension cost. Lastly, at 250 grams, we have the extension going to 54.5. When we subtract from original 35.2, we have 19.3 as the extension cost. Therefore, we can check as the force causing the extension increases, then we have the extension also increasing. We have the extension also increasing. And so, if a graph of force against extension is plotted, a graph of force against extension plotted, it gives a straight line through the origin. A straight line which will pass through the origin. We can check such a graph. when we have force here, F in newtons, and the extension it will cause. The extension it will cause, extension E, meters, the extension it will cause. Therefore, we are saying through the origin, we have a straight line, but it reaches somewhere such that it flattens. It flattens. Such that it flattens. At that point where it flattens, we call it the elastic limit. It is a point where any addition of weights on the spring does not cause further extension. Instead, it can lead to the deformation of the spring. And we say such a material, such a spring, has reached its elastic limit, the point whereby no matter the force added, then more stretching cannot occur, or more extension cannot occur on the spring, and we say it is at its elastic limit. At its elastic limit. Further addition of weight can lead to deformation of the spring. So now, with that, knowing that the more the force exerted on a substance, then the greater the extension which will be caused. We can write the Hooke's Law. It is a conclusion which was made by a scientist called Robert Hooke. That's how we call it. Therefore, the experiment was first done by Hooke. And Robert Hooke summarized the law, and he said that for a helical spring, or any elastic material, the extension costs, the extension produced is directly proportional. Directly proportional to the force causing the extension. The force causing the extension. Therefore, mathematically, we can say that the force causing an extension is directly proportional to the extension it will cause. This implies that if we write force and we do away with the constant of proportionality, then we can introduce an equal sign and a constant k, extension. Therefore, force is equals to a constant times extension. So k is a constant, called the spring constant. The spring constant, and is uniform for a given material. It is uniform for a given material. Therefore, each material has its own spring constant. Each material has its own spring constant. Again, the spring constant is determined by a few factors like the diameter of the wire, the material making up the wire, among other factors. Okay, so now because we are saying is equal to spring constant times extension, then we can also say that the spring constant is equal to force by extension. So we know that force is in newtons and extension is in meters. Therefore, the SI unit of spring constant is Newton per, or Newton per meter, expressed this way. Therefore, the SI unit of spring constant is called Newton per meter. In the next lesson, I'll be doing some examples on Hooke's Law. Thank you for following. Subscribe to Shifting Grades and share our link. Thank you.